Okay, so I've got a couple of things I want to accomplish today. One is to cover our last topic of Unit 1 here, which is variation. And then I want to go back and review. Some people were struggling with the hip and valley rafter calculation. So I want to go back and go through some of that again and give you a chance for those of you that haven't turned in that quiz to get that done. Or if you have turned in that quiz, give you a chance to redo some of the problems you got wrong. So anyway, today we're going to talk about variation. And variation describes how two or more values, variables, interact with each other. There's two main types of variation, and then there's other named types, but they're just really just combinations of those first two. So the first type of variation we want to talk about is direct variation. And direct variation is simply that. If we have two variables, just call them x and y. If x gets larger, y has to get larger in some proportional amount. Or if x gets smaller, y gets smaller in some proportional or related amount. It is proportional. Now, the term proportional means it is a constant ratio. So, in other words, the ratio of y divided by x equals a constant. I'll use k for the constant because we use c for so many other things. Now, a little bit more useful way of writing it, an alternative way, is to write it as y equals a constant times x. That's very useful in a lot of different situations. If we are told that y is directly related to x, that's really all it is telling us is this right here, or this, saying y is equal to a constant times x. Now, there's other wording rather than directly related to x. It could say y is, or y varies, directly with x. That's saying the same thing, but we might have more information. Right? We're told when y is 27, x is 9. Now we have more information. We can further define that relationship here. So y varies directly with x is just telling us the same thing. Y equals a constant times x, or y equals kx. This second piece here, when y is 27, x is 9, that's called an initial condition or a known condition. In engineering, it's very common. We know the relationship. That's what we had here. And you take a known condition, or an initial condition, sometimes called, where you know the value of the variables at that moment in time, and you use that in this relationship here to further define it. So when y was 27, I'll put 27 in for y. X was 9, so I have k, but I'll put 9 in for x. I can now solve to figure out what k is. If I divide by 9 here on both sides, I get 3 equals k. So that means I can combine that with my initial form of this relationship. Instead of y equals k times x, my relationship is actually y equals 3 times x, or y equals 3x. So we have defined our relationship in a little bit more detail. Excuse me. Apparently I got a little bit of a cold coming on. Okay, so anyway, that extra information allows us to further define the relationship. Now we can go further. We can have situations where we have more information or a question being asked based on this information. That might look like this. Y varies directly as X. Now saying directly as X or directly with X means the same thing. I might say when Y is 42, X is 6. And I might go on to ask, find Y when X is 11. So here, again, we're told Y varies directly as X. That's saying Y equals a constant times X. Y equals Kx. And then we have that known condition. When Y is 42, X is 6. So put 42 in for Y equals K times, we put 6 in for X. Now we can divide by 6 to get that 7 equals K. Now we can use that to further define our relationship here. Y equals Kx becomes Y equals 7x. And then the problem further goes on, find Y when X is 11. So I put 11 in here for X. So 7x is 7 times 11, giving us that Y equals 77 when X is 11. So this is a problem that happens a lot in engineering and problem solving, where you don't necessarily know the formula that relates to variables, but you know the type of relationship. You know whether it's direct relationship or some other type of relationship. And you have a known condition. You know that this is true. So then you know, because of the relationship, you know that if you change one of the variables, you know how the other one is going to react to it. So it allows you to do that simple calculation. We might have P varies directly with square root of M. When P is 35, M is 25. Find P when M is 64. A little more complex here. It's not just the two variables related to each other. It's P varies directly not with just M, but with the square root of M. So instead of P equals a constant times M, it's P equals a constant times the square root of M. So we have to modify our formula. It's not relating the variables, it's relating one variable to the square root of the other. But it still works the same way. So that was defining the relationship here. Next we have that known condition. P is 35 when M is 25. So we fill those numbers in. Now it's going to take a couple of steps to solve this. It's not going to be quite as simple as before. First thing we have to do is take the square root of 25, which is 5. Now we know that it could be 5 or negative 5, but in most real applications it's the positive number. So we're only going to use the positive number, the 5. And then we'll divide by 5, get that 7 equals K. So if 7 equals K, we'll go up here and redefine that relationship. P is equal to, instead of K, we'll put in 7. So P is equal to 7 times the square root of M. Now then, we're asked find P when, I forgot to put the M in there, when M is 64. So P equals 7 times the square root of, in place of M, we put in 64. And again, it's just a matter of working it out. So we have the square root of 64 is 8 or negative 8. Again, we're just going to focus on the positive result, just the 8. And then we multiply. P equals 7 times 8 is 56. So P equals 56. The second type of variation is called inverse variation. In an inverse variation, we're going to take two values again, x and y. If x gets larger, the other value has to get smaller in a related amount. Or the opposite is true. If x gets smaller, the other value gets larger in that related amount. So they do the opposite. This is often called a constant product. What that means is x times y is equal to a constant. The alternative is to divide both sides by x to get y equals a constant divided by x. Up above, for direct variation, it was y equals a constant times x. Here, for inverse variation, it's y equals a constant divided by x. Now, there is another form. Another set of terminology, I guess, that goes with this would be called inversely proportional instead of inversely related. Inversely proportional is kind of a misnomer because it's not proportional. It's not a true relation. The ratios are not equal to each other. But what happens is, up above in a direct relationship, if I have the ratio of x1 to y1, the first set, that's going to be the same ratio as x2 to y2. They're proportional, constant ratio. Well, down here, that's not true. If I have the ratio of x1 to y1 for one value, the other ratio will be inverted, hence the term inversely. Inversely means to invert or flip over. So the second value of y will be on the top and the second value of x will be on bottom. Notice that is upside down. Over here, x was on top. Here, x is on bottom. I don't like that terminology because it's not a true proportion. Remember, we taught proportions have to have the link across and the link up and down. We screwed up one of those links when we invert one of those ratios. So to me, inverse variation makes way more sense to look at it as that constant product. Let me show you how we mean that. So we might look at y varies inversely as x. So that's saying now that y is not k times x, y is k divided by x. It's that inverse relationship, that inverse formula. I'd be told y varies inversely with x. When y is 6, x is 8. So y varies inversely with x is still y equals k over x, just like it was up above here. When x is 6, or when y is 6, x is 8. Well, this is that known condition, further defining the relationship. So we can put in 6 for y, 8 for x. Now we can solve this relatively easy for k by multiplying by the 8. If we multiply by 8 on both sides, on the right side, the 8 cancels out. On the left side, 6 times 8 is 48 equals k. So that tells us we can combine it with our initial form up there. Y equals k over x is actually y equals 48 over x. Is the further form or the more exact form of that relationship. We might be told y varies inversely as x when y is 8, x is 9, and then we might even be told find y when x is 6. Y varies inversely as x. Once again, that means y equals k over x. When y is 8, x is 9. That's that known condition. So we put 8 in for y, 9 in for x. And we'll solve for k. Multiply by 9 on both sides gives us that 72 equals k. And so to bring that back up to our original form of our relationship, y equals k over x becomes y equals 72 over x. And now we're asked to find y when x is 6. So we put 6 in there for x. 72 divided by 6, y is 12. So again, we can use that relationship and a known condition to expand it to other situations. There's something called combined or joint variation. And it might read something like this. P varies directly with the square of t and inversely with d. When t is 3 and d is what do I put down there? We'll go 4. P is 18. Find P when T is 5 and D is 2. So once again, we've defined a relationship here, but it's more than two variables. But the relationship between one main variable is defined to the other variables. So P varies directly with the square of T. So that means P equals a constant times the square of T is written as T squared. Inversely with D, so that's the constant divided by D, so we just do that. So that's telling us P is equal to K times T squared over D. Next, we are given T is 3, D is 4, and P is 18. We can use those to find the value of that constant. So 3 goes in for T. D is 4, so 4 goes in for D, and 18 goes over there for P. Now there's a little bit of work to solve this. First, we would want to square the 3. 3 squared, or 3 times 3 is 9. Now we can multiply by the 4 to get rid of the 4. 72 equals k times 9. And we can divide by 9. 8 equals k. So we can take that up here to our original form. If the constant is 8, then p equals 8 times t squared over d. They go a step further, find p when t is 5 and d is 2. So we're looking for p when t is 5, so that's 5 squared, and d is 2. Well, we have some work to do. We're going to do the 5 squared, which is 25. 8 times 5, or 8 times 25 is 200. 200 divided by 2 is 100. So P equals 100 when K is 8, when T is 5 and D is 2. So that is our variation stuff. There is a worksheet attached in Blackboard. On this variation stuff, make sure you look through that. There's two sides to it. Make sure you do at least the front side. The back side has some word problems that are a great way to learn how to apply these concepts. But direct variation and inverse variation comes up a lot. In construction, the biggest example we have of direct variation is what we've been doing with our trusses. If I have an 812 slope on a 36-foot span truss, the height and my run, of course here being 18 feet after 36, have to be proportional or directly related. The bigger the run gets, the bigger the height's going to get, as long as our slope stays the same. So that's why we were able to do that slope of 812 equals h over 18. We could have done rise is directly related to the run. The rise, we can say rise is k times the run. We put in 8 for the rise because it's an 812 slope equals k times 12. We could have divided by 12, get that 2/3 equals k. So that's saying the run, or the rise, is 2/3 of the run. That's rewriting this formula, rise, k is 2/3 equals 2/3 times the run. So I could put in h is my rise, that's my height that I'm looking for, equals 2/3 times 18. 2/3 times 18 is 12. That's 12 feet of height, which is exactly what we would have got here if we cross multiplied and divided. Now this variation was a little bit more complicated method of going about it. I would stick with just writing the proportion, but we could use the direct variation. We know that if the run gets larger, the height has to get larger. That those two values are directly related if our slope stays the same. Inverse variation is more in the heating and cooling side, a little bit in the mechanical automotive side. Pressure and volume. The pressure of a gas at a single temperature was at a constant temperature. The pressure of a gas is inversely related to the volume. So what does that mean? Let's say that we have at 30 psi. The volume is 120 cubic inches. Right, find the volume at 40 psi. So we know here that y equals k times x, but y is going to be our volume, and x will be our pressure, so P, so V equals K times P. So in the initial condition, we have 120 cubic inches equals K times 30 PSI. We divide by 30, get 4 equals K. Oops, I wrote that wrong, didn't I? This is not direct. It's not K times P. It should be K over P. Sorry about that. This is inverse. So it's K divided by P. And so we'll put in 120 cubic inches equals K over 30 PSI. Now we would multiply by 30 to solve that to get 3,600 equals K. So the relationship up here is that the volume equals 3,600 divided by the pressure. So when we change the pressure to 40 psi, the volume is 3,600 divided by 40. Well, 3,600 divided by 40 is 90. So that's going to be 90 cubic inches. So we can see the relationship between the pressure and the volume. Great example of this in construction would be, we've kind of looked at this example before. Let's say you excavate a foundation for a house and you come back and it's rained and it's filled with water. So if you need to figure that out, how long it's going to take to drain with different pumps, we've done this before. The time to drain a pit of water is inversely related to the size of the pump. If a 9 CFM pump can drain the pit in 60 minutes, how long would a 12 CFM pump take? So this is obviously a very classic inversely related problem. The pump gets larger from 9 to 12 CFM, the time's going to get smaller. If you move faster, you take less time to get there. So we look at this as time equals a constant divided by, I'll put in just P for the size of the pump. We had 60 minutes equals a constant divided by 9 CFM. If I multiply by 9 on both sides, I get that 540 equals K. So that tells me I've got the time equals 540 divided by the pump size. So if I want to know what that does for a 12 CFM pump, 540 divided by 12 is going to be 45 minutes. So there are a lot of applications where this applies. Both of these, direct or inverse variation, applies in mechanics and construction and all sorts of the trades. Okay, so I promised we would, after covering that variation, again, there's that worksheet posted on Blackboard for that we would talk a little bit more about the hip and valley rafters and maybe stairs if we get time. So let's talk about hip rafters. So hip rafters, we're just looking at a single roof. If I tell you that the slope up here, let's say that's an 812 slope. We have a span here of 36 feet. And I give you the setback is equal to 12 feet. The first big question is this a conventional hip? Are those slopes the same? Well, the answer, of course, is no, they're not the same. Because if the slopes were the same, the setback here would have to be half of the span. Half of 36 would be 18. So these are not the same slopes. So we're going to start out with the common rafter. A common rafter is a span of 36 feet and a slope of 812. So our first thing we're going to find here is the height. And of course, we find that off. We've got a run of 18 feet, half 36, and our slope of 812. H is the rise, that goes with the 8. 18 is the run, that goes with the 12. And we can cross, multiply, and divide. 8 times 18 divided by 12 gives us a height of 12 feet. Now we'll find the length of that common rafter here. That's going to be the square root of 12 squared plus 18 squared. $21.633. So that is right here. This is 21.633 feet for that common rafter. We have all the information. We could actually find the decrease on the common rafter right now if we wanted to. So let's go ahead and do that. I'll call this next piece here. Go ahead and get out of the way. Call this next piece here Y. We know this distance is going to be 10 feet if we have 2-foot spacings. Y and 10, and then I've got the larger one. It's my setback of 12 feet and 21.633 feet. So I have the proportion. 12 goes to 10 is 21.633 goes to Y. These two sides are related as those two sides are related. And we can cross, multiply, and divide to find Y. So times 10 divided by 12 gives us 18.028 feet. So the decrease on the main roof side is going to be found by subtracting those two numbers. 21.633 minus that next longest jack of 18.28 or 028. So we subtract there. what is this? 3.605 feet. I'm going to trust you can turn that into feet, inches, and sixteenths at this point. So 3.605 feet. Now we have to look at the other side, the hip roof side. First piece of information we need there is the length of this longest hip rafter. Or longest hip jack, I should say. The hip rafter is technically the one that goes down the corner here. Find the length of that longest jack. That's this one again. We're going to look at the side view of it. Looks like this. Our setback is 12 feet. We know that. The height is the same as the height of our common. That's also 12 feet. So this length out here of that longest jack is the square root of 12 squared plus 12 squared. Giving us 16.971. So that length here, 16.971 feet in length. So then we're ready to find that next jack here. I'll link that next jack Y. Of course, this is 18 feet, half the span. This is going to be 16 feet, 2 feet less. So this is 18 feet and 16.971. This will be 16 feet and X, giving us the proportion 18 goes to 16, as 16.971 goes to X. We can cross, multiply, and divide. 16 times the 18.971 divided by 18. 15.085. So our hip side decrease is going to be that difference. 16.971 minus 15.085. 6, 11, so that's going to be 6, 8, 16, 8, 8, 1.886 feet. And again, I'll trust you can turn that back into feet, inches, and sixteenths. So that was an unconventional hip where I gave you the slope of the main roof, the setback, and the span. And we were able to find the decrease. And notice because they were different slopes, there's a different decrease on the main roof side and the hip roof side. If they're both the same slope, that decrease would be the same on both sides. On the quiz, with the hip or valley roofs, problems 1 and 3, they are conventional. They both have the same slope, so it's the same decrease. So there's only one answer for problems 1 and 3. Problems 2 and 4, well, number 2 is very similar to this one. It's a hip with different slopes, so there'll be 2 answers. And for number 4, it's a valley with different slopes, so there'll be 2 answers. So let's do an example of a valley that's unconventional. Different slopes. So here's my L roof, and what I'm going to do to define my different slopes is I'm going to match my peak. So let's say that this here is a 612 slope on a 42-foot span. I'll call this down here 21-foot span. Let's make it more reasonable. Let's make it modular, or closer to modular. We'll call it a 20-foot span. We start with the main roof, finding that common rafter. We do have to label that main roof now because there will be a common rafter in the L roof now too. It's going to be a lot smaller, and in this case we don't know the slope, so we can't start with that L roof rafters. Span of 42 feet, 612 slope. First thing we got to find here is the height. I'm going to use this run of 21 feet. Slope of 612 equals h over 21. Cross multiply and divide, we get that h is 10.5 feet. Now I'm going to leave that as a decimal for right now because we're going to use it. Find the length of that rafter, which will be the square root of 10.5 squared plus the run of 21 squared. Second square root, 10.5 squared plus 21 squared. We'll take the square root of all that. We get 23.479. Oops, is there a question? Okay. So 23.479 feet for the common. So that is this length right here. $23.479. Once again, we actually have enough information to find the decrease there. We know this has to be half of this other span, so that's 10 feet. So the next one here, we'll call that y, has to be at 8 feet. I'm just going to draw those over here. I have 10, 23.479, 8, and y. 10 goes to 8. This 23.479 goes to y. Cross multiply and divide. 23.479 times 8 divided by 10 gives me 18.783 feet. So the decrease there, the main roof decrease, that difference, 23.479 minus 18.783, 6, means I give us 9, 6, and 3. So 3.696 feet. Once again, I'll trust that you can turn that into feet, inches, and sixteenths. Now we have to go back to the L roof. Need to find that length. Well, what I know about that is that it's on a 20-foot span, and the height has to be the same as the height of our common, 10.5 feet. So the length of that piece, oops, I'll do the right color, that length piece of that piece is the square root of 10.5 squared plus 10 is half of the 20. That's a run of 10 feet there. Square root of 10.5 plus, oops, 10.5 squared plus 10 squared, and then we square root that, gives us 14.5 feet. So this here is 14.5 feet. And we know that this distance here is half of that span, half of 42, so that's 21 feet, which means the next one up here, I'll call that length x, is going to be at 19 feet. So we have, going this way, we got 21 feet and 14.5. I'll have x and 19. So I know 21 goes to 19 as 14.5 goes to x. And we cross multiply and divide. 19 times 14.5 divided by 21, we get 13.119. So the L roof decrease will be the 14.5 minus the 13.119, giving us 1.381 feet. Again, I trust you can turn that into feet, inches, and sixteenths. So there would be our two answers. 3.696 feet would be the decrease from one jack to the next on the main roof side, and 1.381 feet is the decrease from one jack to the next on the L roof side. So as you're looking at that quiz, hopefully that helps a little bit. I know the few that I had graded were not looking that people were struggling with that. So even if you've turned it in and it's been graded, you can redo the quiz. You might not be able to submit it through Blackboard again, but email it to me and I will regrade that for you. Right now, you have that homework worksheet. There is a quiz that'll be on Monday. That quiz on Monday will be on this variation stuff that we just talked about. And then test 1, the unit 1 test, is also on Monday. One of the disadvantages of a 2-hour class is we squeeze a quiz and a test on the same day. On Monday, I will still do some items going over more of these hip and valley calculations and stairway calculations if needed. And then hopefully at some part of the hour or some part of the time, we will get started with new material. So I will do some new material on Monday as well, since it is our one day together in the classroom. With that, I'll shut the recording off and let you guys have the rest of the time to work on the homework from that worksheet or on any of those quizzes. I will be on the network to help out if you have any questions.